भी अपनी टांग
Hello, am I audible? So we will wait for 5 minutes and then we'll start. Uh, are you able to listen my voice? Kindly confirm it.
Yes, sir.
Okay, we'll wait for 5 minutes and then we'll start. Kindly mute yourself. Ivarani continue. Hello. Hello. So
Hello.
yes, is am I audible? Yes. Okay. So good evening, everyone. So this is the course named as Advanced Power Electronics and Control. So I am your TA for this course, Abhishek Munshi. I am from IIT Jodhpur, from the Transportation Electrification Lab. So basically, this course is about the advanced power electronics. I hope you all know a basic of the power electronics systems, and then we'll start with this class a little bit of the basics of about the switch and all. So today we'll discuss about the power switches, a little bit about what type of switches are there in the power electronics, and we'll solve some problems that are related to the assignment one of your course. Okay.
I have a question. The course has record. The
Sorry,
course.
again, get you.
Mm, the lecture has record.
Yeah, the course will be recorded and this class will be available at YouTube. I will share the link. Okay.
Yeah, thank you. Thank you. Thank you.
Okay, fine. But try to attend the class online because if you have any doubt, you can ever ask on that because okay. So I hope you already watched the videos which are related to this week, and I will give you a brief summary about that. So that are related to the concept of the switch. So if you see that, if you here, we consider in power electronics we have to design mainly the power converters, right? You have to design the power converters. It may be a DC-DC converter. It may be a AC-DC converter. Maybe a AC-AC converter. So whatever converter you are going to design, you should have to be basic knowledge about the switches which you are using over there, because that are power switches is slightly different from the switch you have already learned in analog and all. Okay. So basically, power switches can be categorized into different way. For first of all, if you consider that it can be divided into uncontrolled switch, semi-controlled switch, and fully controlled switch. Okay. So if you're going deep into the uncontrolled switch means that the switch whose on state and off state is not in our hand. We cannot able to on it or off it by our means, but it can be on and off by itself. Okay, so that is an uncontrolled switch. That because that cannot be controlled by using any kind of control pulse or anything. Okay. So for example of the uncontrolled switch, we can give the example of a diode. As you see here that in case of a diode, this is our anode and this is the cathode of the diode, and whenever the anode voltage is greater than the cathode voltage, it starts conducting, and whenever it is less than that of cathode voltage, it doesn't conduct. So when the diode conducts, it acts as a short circuit, so it acts as a closed switch, and when the diode doesn't conduct, it acts as a open switch. Okay. So basically, this is an uncontrolled switch. As I say that whenever the voltage level is greater or lesser than that basis, the switch will be operated, but we cannot control it by ourselves. Okay. So it depends upon the cathode and anode voltage. Okay. So the diode which we are considering here is something different from that of the signal diode which we had studied previously in other courses. So let me give a brief introduction about that. So if we add a slide here, so see, uh, I hope you all know a little bit about the signal diode. So what happens in the signal diode? There are two paths, that is a P and an N junction, right? And based on which there is this one is anode and this one is the cathode of the diode. Okay, but In case of the power electronics, we are using high power switches. So this kind of diode are different than that of the signal diode. So this is a power diode. There is slightly difference between this diode. There is an N plus N minus doping over here. This is a P plus doping. So this is anode, this is cathode. What is the exactly difference here? There is a lightly doped N section. Mm, this is can say this is a doped N doped section which is not present in our signal dope diode. Okay, and due to which the power diode has a power rating up to suppose kilovolt, ampere rating it may be ampere to kiloamp range, wattage rating is wattage to kilowatt. Okay. Whereas we see that in case of signal diode, the maximum voltage we found is 15 volt, the withstand capacity, and the current rating is somewhat around microampere to milliampere. The power handling capacity is around milliwatt to wattage. Okay, so that's why a power diode has a very high rating than that of the normal diode. Okay, so in power diode, there is we see that there is an additional section. There is one lightly doped N section. Okay, and this doping is obviously proportional to the conductivity of the diode. As if the doping is more and more less, the conductivity will start more and more. Why? Because that was the basic behind the diode. If you see that there's a P plus, this is N minus and N plus junction. If we connect it like this in forward bias, so unless and until this barrier, potential barrier will destroy, the current will not able to flow, right? So this is called the depletion width. So depletion width if increases, then there will be less probability of going up the current, right? But in this case, the width of the depletion increases, and since it is a lightly doped section, so as if the depletion region started increasing, the high voltage withstand capacity is there, because up to a certain high voltage it can able to withstand, and after which this depletion width became narrower, and this is a breakdown will happen and current will able to flow. So that is the principle behind the power diode rather than of the say signal diode, and rest of the things are similar. So this is the IV characteristics of a power diode. So you can see that uh, in forward bias the anode is positive with respect to the cathode. As I say that Va when greater than out of Vk, then the current start flowing. Obviously, suppose in case of a signal diode also we know that whenever we connect it in this way, then current flows in this direction. So it is forward bias, and when it is reverse, then it is in reverse bias. So in case of the reverse bias, what happens? The cathode is positive with respect to the anode, and generally the diode doesn't conduct, but it experiences a small amount of current in the reverse direction due to the reverse leakage or reverse saturation current we called it. And after a certain voltage, there is a breakdown will happen, and it goes into the reverse bias state. So this voltage up to which the reverse current withstand capacity is there, this voltage is called the reverse voltage or reverse breakdown voltage. Okay. So in case of the signal diode, the threshold voltage we know that in case of germanium it is around 0.3 and silicon is 0.7. But in case of the power diode, this threshold voltage after which the forward bias current started rising and rise, this is called threshold voltage. In case of power diode, it is around 0.8 to 1 volt. So power diode can be categorized into three part. Okay. So I will go into that in later. So And this curve, if we do a piecewise linearization of this curve, we will get like this. So this is the forward piecewise linearization of the diode curve, where you can see that it can be linearized as a straight line. So we can able to write it like a equation y equal to mx, and from where we can able to calculate this resistance. This is voltage. This is uh, current. So you can able to calculate the resistance from it, and that is called the dynamic resistance of a diode. Okay, and the power diode can be categorized into three types, mainly which are using in which we you will use in power electronics. There are three types of diode which we are use. One is the general purpose diode. General purpose diodes, they have high reverse recovery time. Their current rating is around, suppose if 1 amp 2 amp current ratings are available, IN suppose 4008, this is a general purpose diode. Voltage rating is 50 volt to 5 kilovolt voltage rating, 3 volt to 5 kilovolt. So in this range you will find some diode like 1N4008, 1N4007, etc. So these are general purpose diode. Next, another category is fast recovery diode. Fast recovery diode which has a low reverse recovery time. Obviously it is fast, so it has a low reverse recovery time, and it has a voltage rating around 50 volt to 3 kilovolt. So this kind of diode we generally we use in making rectifier circuits, fast recovery diode. Another category which we generally use in case of the DC-DC converters, in buck converter, in boost converter, there are diodes which we use. Generally, we use a very fast recovery time-based diodes, very fast recovery time-based diode that is very popular, known as Schottky diode. Suppose one in 5808, this type of are Schottky diodes. 5819. It's very popular, 1 amp 40 volt around range. So these are the types of diodes which we use, and diodes are fallen into the category of uncontrolled switch because we cannot able to control it by ourselves. Okay. Next is semi-control switch. In case of semi-control switch, the example is silicon control rectifier or thyristor, because here what happens in silicon control rectifier, we can able to switch on it, but we cannot able to turn off it by ourselves. Okay, so if we're giving a voltage that is greater than that of the gate turn on voltage, then the SCR will turn on, but it will not turn off. So you have to turn off by means of some processes that are called commutations techniques. I hope you'll that were covered in these are not in this syllabus. So but you can able to turn off SCR by some method commutation techniques like DVDT triggering and natural commutation and all. Okay. So in SCR there are three modes. One is reverse blocking mode, one is forward blocking mode, another one is forward conduction mode. Okay. So this is the IV characteristics of SCR, where if you see that initially it is in a forward blocking mode, and whenever this gate turn on voltage is greater than that, then it started moving. So that is forward uh, conduction mode. And if it is less than that, then it will be in forward in reverse blocking mode. And after a certain voltage, in case of diode similar to the diode, there is a reverse breakdown voltage after which the switch will closed. It will break down. Okay. So this is an example of a semi-control switch. Next category of switch is fully controlled switch. Basically, this type of switch we use in designing the power converters like inverter and buck converter, boost converter. We have to use this kind of switch. There is a fully controlled switch. What happens in fully controlled switch? There is a, suppose an example is MOSFET. In MOSFET, IGBT, this kind of switch, there is a gate, and in gate we have to give PWM signals like pulse width modulated signal. Whenever it is on, then it is on. Whenever it is off, it will be off. By giving it into the gate, we can able to control the switch. So that's why on and off both are controlled. So this is called fully controlled switch. This is a MOSFET. A MOSFET can be of two types: P channel MOSFET, N channel MOSFET. So that depends upon the enhancement MOSFET. The enhancement MOSFET can be defined by off state where there is no gate voltage, and on state when there is a gate voltage. That is just something different than that of we think of it. It is off state whenever there is no gate voltage, and it is in on state whenever there is gate voltage. Naturally, it's conducting. Okay, so it will be off at zero gate source voltage and on at zero gate source voltage at the same time. So there is depletion mode is whenever it is on, and whenever it is off, it is called enhancement mode. Okay, and E channel and actually N channel and P channel means that is a positive channel and there is negative channel. Okay. Another beautiful concept of power MOSFET is that in case of the power MOSFET, there is an inbuilt body diode. We assume it that in that way. Suppose this is our MOSFET, and there is a body diode. So that's why basically MOSFETs are bidirectional switches. So what happens in this case, you will see that this is an N plus and N minus, and there is a P well where there is a N dopings are done to make the MOSFET, and this PN basically makes the body diode of the MOSFET. So that is an intrinsic property of the power MOSFET. In power MOSFET, there is an inbuilt body diode like feature. So it acts as a bypass path where if the current can flow back, that is a freewheeling diode. So from where the freewheeling current can move out. Okay. So in signal MOSFET, if you have learned that in analog and all, then we can see that there is a MOSFET, but in that case there is no body diode. But in case of the uh, power diode, this feature is there. Okay. In fully controlled switch, one of the another example, famous example is IGBT. This basically IGBT has the property of both the bipolar junction BJT and MOSFET. So if you see the simplified equivalent diagram, if you able to see that there is a BJT, there is a MOSFET, both are connected to make the IGBT. Okay. In IGBT, there is no such kind of body diode and all, so this is not an bidirectional switch, but we use it in case of designing inverter and all. So in that case, we have to add a anti-parallel diode in between. Okay, so this was invented by an Indian, Jayant Baliga. So I put the name of here. So the IGBT is also an example of a fully controlled switch. Okay. Nextly, we can categorize switch into unidirectional and bidirectional. Obviously, unidirectional means when uh, a current is flowing at one direction from the switch, and bidirectional means when current is flowing from both the direction from the switch. So as I said here, you can able to see it that in case of unidirectional, if you draw this diagram, it can conduct in one direction. The current can conduct in one direction, but in bidirectional, the current can conduct in both direction. The red uh, line shows that it can conduct in both direction. Okay, so for example, MOSFET, as I said, it has an inbuilt diode, so current can flow in this direction and it can freewheel through this direction. So it has the capability of bidirection. Okay, but in case of diode, the current can flow only in one direction. So this is unidirectional switch. Okay. Again, we can categorize switch into basis of the voltage. But if you have any doubt up to it, you can ask me, and then we can well proceed. If you have any doubt, you can ask. You can write over here up to this part. If you have any doubt, you can ask. It's a very basic. So if you have any doubt, you can ask. Okay, fine. So
Sir.
yes. Okay. Nextly, we can categorize the switch into basis of the voltage, that whether it is unipolar or bipolar. In unipolar, the switch can conduct in one direction of voltage, and in bipolar, the switch can conduct in both direction of the voltage. As you can see, for an unipolar, I'm giving an example for unipolar. This is an example of IGBT. It's a unipolar switch where it can conduct in the forward direction, and it has the capability of forward blocking. And in case of the diode, it has an capability of reverse blocking. So it is both are unipolar. And in case of bipolar, it has capability of both side blocking. That is, it can in forward and backward at the both at the same time. For example, this is MOSFET. MOSFET is a bipolar bidirectional switch. And if we have an IGBT with an anti-parallel diode, IGBT plus anti-parallel diode, then it can able to conduct in both direction. Why? If you see here, if you plus it, then for IGBT we have forward blocking state, and for diode we have reverse blocking state. So if you have both the IGBT and the anti-parallel diode at the same time, then it will act as a bipolar switch. Okay. So at a glance, I'm showing here the basically the quadrants. So you can go through these quadrants for understanding that for a diode is an unidirectional unipolar switch. BJT is also a unidirectional unipolar switch, but the difference is that in case of the diode, there is a capability of reverse blocking, but in case of BJT, there is a capability of forward blocking. Next is GTO, gate turn-off transistor, gate transistor. So it has capability of both the blocking states. So it is a bipolar unidirectional switch. And next, FET, normal with FET, if you consider, then that is an bidirectional unipolar switch. And ideal switch, it can conduct in any direction. So it is a bidirectional bipolar switch. For example, MOSFET categorized into that. So if we go on through the timeline of the discovery, so firstly SCR was invented, after which RCT was invented in 1962, then TRIAC, then BJT, then GTO, after which power MOSFET has come, then SIT, IGBT, MCT. Then now presently they are working on the wide bandgap devices, the WBG devices, mainly SiC and GaN based MOSFETs are used, that are basically different than that of the mm, normal MOSFETs, power MOSFET, because it has a capability of high frequency rather than that of the normal MOSFET range. it can conduct up to a megahertz range. Okay, so these are the basics which are, I think, which are discussed in this week. So if you have any doubt, you can ask. After which we'll start solving some problems that are related to it. Okay. So if you have any doubt, you can ask. Okay, fine. So I hope you don't have any doubt. So this is the first question. So try to answer it in the comment box, or you can unmute and also answer it. If you're able to answer it, then it will be good for yourself also, and it will be engaging also. So the first question is, for similar power rating of the switching device, which one is faster? So I'm giving 5 minutes to try to solve it and answer it. You have to mention the reason also why, because you can. Many of you have answered it, so it is a wrong answer. So the correct answer is, a power MOSFET is a, for similar power rating. I said that which of the switching device is faster. Obviously, the power MOSFET has a majority carrier device, and so it turns off and turn off fast. So keep it in your mind that the power MOSFET can be used for high switching frequency. I also mentioned it that for GAN based or SiC based device, it can be used for megahertz level. So in silicon device, we can use it for 100 kilohertz, 50 kilohertz, 200 kilohertz, up to which is proper. You can able to use it. But if you see, the many of you have answered IGBT, but the switching frequency of IGBT is limited to hardly 20 kilohertz, 15 kilohertz. But there are some modules which you can use up to 40 kilohertz. So that was a wrong answer. So the correct answer is MOSFET. You can answer it in this way, that the switching frequency of MOSFET is very high. So that's why we choose MOSFETs for designing high switching frequency converters. Okay. So is it clear? Okay, fine. Many of you have answered IGBT, IGBT, IGBT. One of you had said that there is a current control device. But what is the function of current control device? So how it can be faster if it is a current control device? Based on the switching frequency, you have to thought about it. Okay. So next, the arrow on the symbol of the MOSFET indicates what? So this is a very easy question. So try to answer this properly and also mention why you're answering that. Okay. try to write the reason also. Don't answer like randomly C, D, A, B, everyone. So fine. The correct answer is the direction of the electron. Okay. So basically, the arrow indicates the direction of electron. Whether it is opposite, uh, actually, direction of electron. If it is the direction of electron, then the current direction will be reverse. Okay. So it indicates the direction of the electron. So in case of P channel, N channel, we'll see that this kind of arrows are there. That means that is the flow of the electron, not the flow of the current. Okay, the current direction will be reverse of that. Okay. So next, which devices do not belong to the transistor family? It's an easy question. IGBT, MOSFET, GTO, BGT. Which of the following is not belongs to the transistor family? Okay. Yeah, Rakesh, you switch off your camera. It doesn't require to switch on, turn on your camera.
Yes, I open the camera. Switch off yellow.
Fine. So many of you have answered it correctly. That is a gate turn off transistor, which is belonging to the thyristor family. So gate turn off thyristor we also call it. So it is belonging to the thyristor family. So thyristor. So that's why this is not a transistor. Okay. Rest of is BJT, IGBT, all are transistor. MOSFET is also transistor type because it has gate drain source is similar to the collector emitter base and collector emitter gate of IGBT. Okay. Next, if the cathode of an SCR is made positive with respect to the anode and no current is applied, then all the junctions are reverse biased, all the junctions are forward biased, only the middle junction is forward biased, only the middle junction is reverse biased. So that depends upon the three state of the SCR, as I said, the forward blocking, forward conduction, and reverse blocking. Try to answer it with proper explanation. See, try to understand it properly. Otherwise, you'll not able to answer it properly, right? So, let me discuss it a little bit. Uh, so this is an SCR. So it has a P junction, and it has a N minus, another P junction, and then there is an N plus junction. Okay. So first, if we consider that we are connecting a negative with this, then what will happen? Uh, Let us consider it has three junctions. One is J1, another one is J2, another one is J3. So if we connect negative with respect to this is anode, this is cathode. If we connect in this way, then what will happen? J1 will be in reverse bias. Fine. J2, since negative is connected to N and positive to P, J2 is forward bias. And again, J3, if you see that positive to N, negative to P, so this is also reverse bias. So this is the state which I said, that is reverse blocking state. Fine. Now we have we connected the positive with the cathode, negative with the positive with the anode and negative with the cathode. And there will be two cases. One is gate circuit is open. Gate circuit means if from here there is a gate pulse and gate pulse is open. When gate pulse is open, then J1 is forward bias, J2 is reverse bias. But J3, since gate is open, so it is in short circuit case. Okay. So this is called the forward blocking state. And now, if this gate pulse is connected with, suppose is positive is negative, when gate circuit is connected, then everything is in forward bias. J1, J2, J3 all are in forward bias, and this is called forward conduction mode. Okay. So now what will be the answer? So the middle junction will be in forward bias because we connected positive with respect to the anode and no gate current is flowing. So in that case, the device is in reverse blocking state and only the middle junction is forward bias, whereas the other two are reverse bias. Okay, clear? Next, at present, the state-of-art semiconductor devices are being manufactured using semiconducting diamond, gallium arsenide, germanium, silicon carbide. So what will be the answer? Okay, fine. So presently silicon carbide devices are used, and also moving into the GaN based device, that is gallium nitride based device. Okay. So as I said, this has very high switching frequency. Silicon carbide devices are used. This has also high switching frequency. But in case of GaN, the selection of gate driver is something difficult than that of the normal devices. Silicon devices are also used in this normal SCI based device. Okay. So next question, in case of a practical PN junction diode, the rise in the junction temperature will, which of the following is, this was discussed in the first slide. So try to answer it. So fine, it will decrease with the width of the depletion region. They said the temperature will excite the charge, which will go and recombine with the charge of the depletion region in its width. So higher the temperature, there will be lesser EMF required to turn on the device. That is, the barrier potential will be less barrier potential required. So higher temperature will decrease the width of the depletion region. Okay. So in a Schottky diode, the aluminum metal acts as anode, cathode, gate, common terminal. Okay. What will be the answer? See, in case of the Schottky diode, as I said, there are three types of diode. That is general purpose diode, fast recovery, reverse recovery diode, and Schottky diode. In case of the Schottky diode, the P-type material is replaced by platinum or aluminum. So that is why anode will be the correct answer. Okay. So Schottky diode, as I said, it is used for low voltage and for high power rating. The voltage rating is around 300, 100 volt. So 1 amp to 300 amp. So Schottky diode, we doesn't use any non-general P-type device, P-type doping. Instead of which we use platinum or aluminum. Okay. See, and another thing which you have to know, that is the reverse recovery time. This is the reverse recovery characteristics of a diode. So we have to know that the reverse recovery time between the forward current and it will vanish as a reverse recovery. That, as I said, that in case of the diode there will be a reverse leakage current. So the time to um, overcome that is called the reverse recovery time. So this is the reverse recovery characteristics of a pipe diode. I mentioned it here because in case of all the three diode, we will say that the reverse recovery time is high in case of general purpose diode. In case of Schottky diode, it is fast, and fast reverse recovery diode, it is faster. And so that's why reverse recovery time is an important part of the diode. We have to understand it. So if you have any diode in reverse recovery time, then you can discuss it in brief. So reverse recovery characteristics we require to understand. In here, see, we have to calculate. There were some formulas you can able to calculate the reverse recovery charge rate from here. So if you see here that this area under this car is the charge, the reverse recovery charge actually. Area under this current waveform. So that is half into IRM into TRR. Okay. So this is the reverse recovery charge. That means the charge present after forward current became zero. Forward current, that is this IF, became zero. Okay. So we can write it like half into you can replace it with IRM. So what see TRR, from here you can able to see that the reverse recovery time TRR is summation of TA plus TB. Fine. And it can also written as 1 plus S of TA. This why? Because TB is S of TA, where S is the softness factor. That means how much softly it can able to come back into its original state. After zero, it is not zero. Whenever it comes down to zero, it is not zero. After a certain time, it will come back into the zero. So this is the time which you require for coming back into the zero. This is reverse recovery time. Okay. So this is softness factor, and if you write it, then IRM, the reverse recovery current, will be di dt into TA. right, is di dt trr 1 plus s. Fine. So if we replace it with IRM here, then it is di dt trr square by 1 plus s. This is the formula for you can derive it for the reverse recovery charge, and this is reverse recovery current. Okay, fine. So next question: if the doping level of the semiconductor increased, then the width of the depletion layer will what happens? As I said, that doping is directly proportional to the conductivity. So think about in that direction and try to answer it. So if the doping level will increase, what will be the answer? It will decrease. Why? Higher the doping means it has more number of charge carrier available to neutralize the opposite charges on the junction. In a simplified way, you can say that higher the doping means the conductivity will increase, and how the conductive it will conduct more and more current. Obviously, its depletion width needs to be reduced. So higher the doping means the depletion layer will decrease. Okay. So next question: which of the following power semiconductor device had bidirectional current capability? So this is very easy for you to answer. Try to answer it. Fine. So what will be the answer? So it is triac. It is not MOSFET. If you have an option like triac, then you have to answer triac. Why? Because as I said already here that MOSFET is a bidirectional switch, but as MOSFETs are often used as a bidirectional switch, but it is not meant for a bidirectional because it acts as a bidirectional. Why? It has an inbuilt body diode. It acts as for freewheeling purpose, so it is bidirectional. But it is not meant for bidirectional. Whenever you have an example like option like triac, you have to answer triac because this is a triac, so it has the combination of two anti-parallel thyristors, so current can flow from here, current can flow from here. MOSFET is also correct answer, but if you have to, and this is an MSQ, then both of these is correct, and this is an MCQ, so the more accurate answer will be triac because while often MOSFETs are used as a bidirectional switch, but they are not inherently bidirectional in nature. Okay. So their channel is bidirectional because due to the in body diode behavior of the MOSFET. So that's why it will act as a bidirectional switch, but it is not inherently bidirectional. Okay, fine. So next question, for a power transistor, if the forward current gain alpha is 0.97, then beta is what? So you have to understand the relationship between the alpha and beta. So I will discuss it and solve the problem. So try to answer it. Try to answer it because it's similar to the alpha beta relation of the transistor in analog. So, okay. So this is the last question. So try to answer it, and after which we will. So see, so what will be the answer? So in case of the transistor, whether it is in CV mode, whether it is in CE mode, you see that there is an emitter based collector. So there are two current amplification factors. One is alpha, one is beta. Okay. So the current amplification factor or current gain in the transistor is the ratio of the output current to the input current. So if the transistor is connected in common base mode, that is in CB mode, then we call alpha as the current gain, that is IC by IE. See what I said, that the ratio of the output current with respect to the input current. So in case of it is in CB mode, the input current is I and the output current is IC. So the current amplification factor alpha will be IC by IE. But in case of the CE mode, whenever it is connected in common collector mode, then the input current is IB and the output current is IC. So that is the current amplification factor is IC by IB. So if we simplify it, we'll get a relationship that beta is equal to alpha by 1 minus alpha. So if we put the value of alpha as 0.97, so the beta will be 32.33. So correct answer is D. Okay. So is it clear to everyone? So that is all for the day. So if you have any doubt, you can ask me. Otherwise, we'll drop the class here. If you have any doubt, you can ask. Otherwise, you can leave. Thank you. That's all for the day. Yes, Somo, I will share the note and you will get it from the NPTEL. Okay. And in the next class, I will share the link also where you can find the note and the YouTube link also. Okay. So fine, that's all. Okay. So good night. We'll meet in the next week at the same time. Okay. Thank you.